Hello students, welcome to grade 12 chemistry revision lesson on common ion effect and buffer solutions. In our today's lesson, we will learn about common ion effect and buffer solution. At the end of this lesson, you will be able to define common ion effect and buffer solution, give some common examples of buffer systems, calculate the pH of a given buffer solution. Common ion effect. Common ion effect is the shift in equilibrium caused by addition of a substance having an ion in common with equilibrium mixture. Consider dissociation of acetic acid CH3COOH. The weak acid dissociates to a small extent into acetate CH3COO minus aqueous plus H plus aqueous. Now this reaction is equilibrium reaction. The reaction is at equilibrium. If you add a substance having a common ion with this equilibrium mixture, then the equilibrium shift. The equilibrium shift. Because according to Le Chatelier's principle, if a system at equilibrium is disturbed, then the system will shift its equilibrium position so as to counteract the effect of disturbance. One of the disturbance mentioned by Le Chatelier principle is addition or removal of concentration of reactants or products. Adding a common ion suppresses the ionization of a weak acid or a weak base. If a substance having a common ion in equilibrium mixture of the weak acid or the weak acid, then the dissociation of the weak acid or the weak base is suppressed. The source of the common ion is typically provided by adding a strong acid. A strong acid. If a strong acid is added to a reaction at equilibrium, then the dissociation of the weak acid is suppressed. A strong base can provide a common ion. A soluble salt provides a common ion. Given this reaction, acetic acid plus water in equilibrium with acetate plus hydronium ion, what happened to the pH of the acetic acid solution if we add sodium acetate? If sodium acetate is added to this equilibrium reaction, then the sodium acetate provides a common ion, which is acetate CH3, provides acetate CH3COO minus, is a common ion. Now concentration of acetates on this side increase, on the product side increase. Equilibrium shift to the reactant side as predicted by Le Chatelier principle. Therefore, concentration of hydronium ion decreased and pH of the solution increased, because hydronium ion concentration and pH of a solution are inversely proportional. If hydronium ion concentration decreases, then pH of the solution increases. Therefore, what happened to the pH of the acetic acid solution if we add sodium acetate? pH of the solution increases. pH increases. pH increases. Examples. What is the pH of a 0.1 molar acetic acid solution? Dissociation constant of the acid is 1.8 times 10 raised to minus 5. Now the acid is acetic acid, is the weak acid. acetic acid, CH3 COOH aqueous slightly dissociates into acetate, CH3 COO minus aqueous plus H plus aqueous is the weak acid. To calculate pH of this solution, we need equilibrium concentration of H plus. Now, initial concentration of acetic acid is 0.1 mole per liter. Initial concentration of acetate is 0. Hydrogen ion concentration 0. Change. Let X amount of acetic acid be dissociated. Its concentration is decreased by X minus X. Concentration of acetate is increased by X plus X. H plus X. Equilibrium concentration of acetic acid is 0.1 minus X. 0.1 minus X. Equilibrium concentration of acetate X. Equilibrium concentration of H plus X. You can set acid dissociation constant for acetic acid. Now Kn equal acid dissociation constant for acetic acid is 1.8 times 10 raised to minus 5 equal equilibrium concentration of acetate is X, equilibrium concentration of H plus again X times X is X squared divided by equilibrium concentration of acetic acid, which is 0.1 minus X, 0.1 minus X. For a small value of X, 0.1 minus X is approximately 0.1. From this, X equal equilibrium concentration of acetates equal equilibrium concentration of H plus, which is the square root of 1.8 times 10 raised to minus 6 equal the square root of this is 1.34 times 10 raised to minus 3 molar. pH of this solution is the negative logarithm of hydrogen ion concentration. pH equal minus log of this is 3 minus log 1.34 equal 2.87. Before adding a substance that provides a common ion, pH of this solution is found to be 2.87 and hydrogen ion concentration is 1.34 times 10 raised to minus 3 molar. Now, what happened to pH of this solution if a substance that can provide a common ion is added to this solution? What is the pH of a 0.1 molar acetic acid if we add 0.05 molar sodium acetate to this solution? Now, acetic acid is the weak acid. Acetic acid CH3 COOH aqueous slightly dissociate into acetate CH3 COO minus aqueous plus H plus aqueous. Initial concentration of acetic acid is 0.1 mole per liter. Initial concentration of acetate is 0.05 because sodium acetate is a salt. Salts are strong electrolytes, completely dissociate into acetate and sodium plus. Concentration of acetate is 0.05. Initial concentration of H plus is 0. Change. Let X amount of acetic acid be dissociated. Its concentration is decreased by X is minus X. Concentration of acetate is increased by X plus X. H plus increased by X plus X. Equilibrium concentration of acetic acid is 0.1 minus X. Equilibrium concentration of acetate 0.05 plus X. Equilibrium concentration of H plus is X. Now you can set dissociation constant for acetic acid Km equal 1.8 times 10 raised to minus 5 for acetic acid equal equilibrium concentration of acetate is this. Equilibrium concentration of H plus X into 0.05 plus X divided by 0.1 minus X. For a small value of X, 0.05 is approximately 0.05 equal X into 0.05 divided by 0.1 minus X is approximately 0.1. Now 1.8 times 10 raised to minus 5 equal 0.05 divided by 0.1 is, this is 5 divided by 10 is 1 over 2x. 1 over 2x. From this, x equal equilibrium concentration of H plus, equilibrium concentration of H plus equal 2 times 1.8 times 10 raised to minus 3. This is H plus 3.6. 3.6 times 10 raised to minus 5. Now pH of this solution is the negative logarithm of hydrogen ion concentration. pH equal minus log of H plus concentration is 3.6 times 10 raised to minus 5. 3.6 times 10 raised to minus 5 equal 5 minus log 3.6 equal 4.44 is pH of the solution after adding a substance that can provide a common ion, acetate. Buffer solution. Buffer solution is the solution that resists change in pH upon addition of a limited amount of an acid or a base. Buffers are used to control pH of the solution. Examples of buffer solution: biological buffers maintain the pH of all body fluids. Best buffer system consists of either a weak acid and its conjugate base, or a weak base and its conjugate acid. Students, buffer solution contains either weak acid, HM, and its conjugate base, A minus, or weak base, B, and its conjugate acid, which is BH plus. BH plus. See? For example, acidic buffer solution, a mixture of acetic acid and acetate is acidic buffer solution. A mixture of ammonia and ammonium ion is basic buffer solution. Ammonia and NH4 plus. For example, identify the solutions below that would make a good buffer solutions. N, HF, and sodium fluoride. This solution is a buffer solution because this solution contains a weak acid, hydrofluoric acid, and its conjugate base, fluoride ion. Sodium plus is the spectator ion. Therefore, HF and its conjugate base, F minus, make a buffer solution, which is acidic buffer solution. Potassium hydroxide and KF, this is not a buffer solution because a buffer solution contains either a weak acid and its conjugate base, or a weak base and its conjugate acid. Sodium nitrate and nitric acid, this is not a buffer solution because nitric acid is a strong acid. Ammonia and ammonium chloride, now this is basic buffer solution. Why? Because this solution contains a weak base, ammonia, and its conjugate acid, which is NH4 plus. Chloride ion is the spectator ion, has no effect on pH of the solution. In acetic acid and lithium acetate is the buffer solution. Weak acid and its conjugate base acetate. Sodium hydroxide and sodium chloride. This is not a buffer solution. Students, now let us try this exercise so that you can practice what you have just learned. You have 2 minutes. Good. How did you do it? Let us do together. Nitrous acid and sodium nitrite is a buffer solution, acidic buffer solution, because this solution contains the weak acid, nitrous acid, and its conjugate base nitrite. You see, nitrous HNO2 and its conjugate base nitrite NO2 minus make acidic buffer solution. B, hydrogen cyanide and sodium cyanide. Again, this is acidic buffer solution because this solution contains weak acid and its conjugate base cyanide ion. You see, HCN and CN minus is acidic buffer solution. C, perchloric acid and sodium perchlorate. This is not a buffer solution because perchloric acid is the strongest acid. A solution is said to be buffer if it contains weak acid and its conjugate base, or weak base and its conjugate acid. This is not a buffer solution. D, ammonia and ammonium sulfate is basic buffer solution. Ammonia NH3 and its conjugate acid NH4 plus is basic buffer solution. E, ammonia and ammonium bromide. Again, this is basic buffer solution because this solution contains weak base ammonium and its conjugate acid NH4 plus. Good. How buffer solution works? How buffer solution resists changing pH? To understand the action of a buffer, consider a buffer that contains approximately equal molar amounts of a weak acid, HA, and its conjugate base A minus. Consider a buffer solution contains a weak acid HM and its conjugate base A minus. Now this buffer solution is acidic buffer solution. When a strong acid is added to this buffer solution, a strong acid like hydrochloric acid is added to this buffer solution, HCl. The added hydrochloric acid provide hydrogen ion, H+, provide H+. It supply hydrogen ions that react with the base. Now the added acid react with the base A minus. Therefore, H+, this is added acid, plus A minus is conjugate base. H plus A minus gives HN. On the other hand, when a strong base such as sodium hydroxide is added to this buffer solution, the added sodium hydroxide supply OH minus. Sodium plus is the spectator ion, has no effect on pH of the solution. Therefore, the added base react with the acid, you see. OH minus react with HN to form water and A minus. Now through this action, through this process, buffer solution resists change in pH. When an acid is added to a buffer solution, the acid reacts with the base. When a base is added to a buffer solution, the added base reacts with an acid. Henderson-Hasselbalch equation. This equation enables us to calculate pH of acidic buffer solution. pH of a buffer solution can be calculated from the Henderson-Hasselbalch equation, which is pH equal pKn is the negative logarithm of Kn plus log conjugate base concentration divided by acid concentration. This is for acidic buffer solution. For basic buffer solution, POH, for basic buffer solution, POH equal pKb plus log acid concentration divided by base concentration. This is for basic buffer solution. This is for acidic buffer solution. The equation is known as Henderson-Hasselbalch equation. Example: what is the pH of 500 milliliter of 0.1 molar formic acid combined with 400 milliliter of 0.2 molar sodium acetate? Students, this is a buffer solution. What type of buffer solution is this? Acidic buffer solution. For acidic buffer solution, the Henderson-Hasselbalch equation is this: pH equal pKm plus log base concentration divided by acid concentration. We need concentration of the base and concentration of an acid. Now, this buffer solution contains the weak acid, formic acid, HCOOH, and its conjugate base, formate ion, HCOO minus. Amount of formic acid mixed with formate is number of mole of formic acid, HCOOH, equal molarity times volume. Molarity of formic acid is 0.1 mole per liter times volume of formic acid is 500 milliliter. You have to convert it into liter, which is 0.5 liter. 0.5 equal 0.05 mole. This is amount of formic acid that is mixed with formate ion, 0.05 mole. Amount of formate ion that is mixed with formic acid equal number of mole of formate, HCOO minus, again molarity times volume of the solution. Molarity of formate is 0.2 mole per liter times volume of format iron is 400 milliliter. In liter is 0.4 liter, 0.4 liter equal, this is 0.08 mole. Now, amount of format mixed with formic acid is 0.08 mole. pH of this buffer solution, pH of this buffer solution equal pKm is the negative logarithm of Km. Acid dissociation constant of formic acid is 1.8 times 10 raised to minus 4. pKm is the negative logarithm of this, which is 4 minus log 1.8 plus log base concentration, base, conjugate base, which is format iron. Concentration by definition is number of mole divided by volume, total volume. Number of mole of format iron is 0.08, 0.08 divided by volume of buffer solution, volume of buffer solution, which is 500 milliliter plus 400 milliliter is 900 milliliter. In liter, 0.9, 0.9 liter divided by acid concentration, concentration number of mole divided by volume of the buffer solution, total volume. Number of mole is 0.05, 0.05 divided by total volume is 0.9 liter. Now this will be cancelled by this. pH of this solution, pH equal 4 minus log 1.8 plus log 8 over 5 equal 3.95. 3.95. This is pH of this buffer solution. What is pH after 20 milliliter of 0.5 molar HCl is added to buffer? What is pH of this buffer solution if an acid is added to it? Now, this buffer solution contains the weak acid, formic acid, HCOOH, and its conjugate base, format HCOO minus. Amount of formic acid in M, amount of formic acid is 0.05, and amount of format 0.08. Amount of this is 0.05. Amount of format is 0.08 mole. To this solution, what is added? Hydrochloric acid. To this buffer solution, hydrochloric acid is added. Now the added acid supply H plus. You see? This acid reacts with the base, format HCOO minus plus H plus gives formic acid HCOOH. Amount of format reacts with the acid is 0.08, 0.08 mole. Amount of added base acid is molarity times volume. Number of mole of H plus is molarity times volume. Molarity of the added acid is 0.5, 0.5 mole per liter times volume is 20 milliliter. In liter, 0.02. This is the same as 0.01 mole. 0.01 mole. Now H plus is the limiting reactant because it is found in small amounts. Amount of product is determined by the limiting reactant. From this reaction, 0.01 mole of formic acid is formed. Now this is in excess. Unreacted formats, HCOO minus equal 0.08 minus 0.01 is 0.07 mole. Produced formic acid is 0.01 mole. There is formic acid in a buffer solution. Now total formic acid, total formic acid, HCOOH equal 0.01 plus 0.05, which is 0.06 mole. The solution is still buffer solution because it contains weak acid and its conjugate base format. We can use Henderson-Hasselbalch equation to calculate pH of this solution. Therefore, pH of this solution equal pKm plus log base concentration divided by acid concentration, which is pK plus log base divided by acid. This is 4 minus log 1.8 plus log base concentration. The base is 4-methane. Its concentration is 0.07 divided by volume of the buffer solution. 500 plus 400 milliliter plus 20 milliliter is 920 milliliter, which is log base concentration 0.07 divided by total volume is 0.92 liter divided by acid concentration. Acid is 0.06 divided by total volume is 920 milliliter in liter, 0.92 liter. Now this will be cancelled by this. Therefore, pH of this solution, pH equal 4 minus log 1.8 plus log 7 over 6. 4 minus log 1.8 plus log 7 over 6, which is 3.81. 3.81 is pH of a buffer solution after adding 20 milliliter of 0.5 molar hydrochloric acid. Yes. Before adding any acid, pH of the solution was found to be 3.95. After adding a small amount of an acid, pH of the solution, this buffer solution, is found to be 3.81. Small change in pH. That is why buffer solution is a solution that resists change in pH upon addition of a limited amount of an acid or a base. See, what is pH after 20 milliliter of 0.5 molar sodium hydroxide is added to a buffer? Students, now let us try this question so that you can practice what you have learned. You have 2 minutes. Good. Welcome back again. How did you do it? Hydrolysis of salts. Hydrolysis of salt is reaction of ions of salt with water to produce hydronium ion or hydroxide ion. 1. Salts of a strong acid and a strong base. Hydrolysis of salts of a strong acid and a strong base. Example, sodium chloride. Now this is a salt derived from a strong base, sodium chloride. Sodium chloride is the salt derived from strong base, sodium hydroxide, and strong acid, hydrochloric acid. Now, what happened to pH of this solution if sodium chloride is dissolved in water? If the solution become acidic, basic, or neutral? Let us see it. Sodium chloride is a strong electrolyte. Is the salt, sodium chloride, completely dissociates in water into sodium plus aqueous and Cl minus aqueous. Now, hydrolysis of a salt is defined as reaction of ions of salt with water to produce hydronium ion or OH minus. Now sodium plus water. No appreciable reaction. No reaction. Because cations of alkali metal and alkaline earth metals do not react with water. Cl minus plus water. Again, there is no reaction. Why? Because Cl minus is the conjugate base of a strong acid, hydrochloric acid. If an acid is strong, its conjugate base is weak. Now Cl minus has no tendency to accept a proton from water, no affinity for H plus. Therefore, if a salt derived from strong acid and strong base dissolve in water, pH of the solution is unaffected. pH of the solution is 7, neutral solution. pH is 7, neutral solution. 2. Salts of a strong acid and a weak base. What happened to pH of the solution if a salt derived from strong acid and a weak base dissolve in water? Consider these salts: ammonium bromide, NH4Br. This is a salt derived from weak base ammonium, and strong acid, hydrobromic acid, HBr. If this salt dissolve in water, it dissociates into NH4 plus Br minus. Now, hydrolysis of salt is reaction of ions of salt with water. Therefore, NH4 plus water, H2O liquid. Now this is an acid. Acids are proton donors. Gives ammonium, NH3, and hydronium ion, H3O plus. Br minus plus water. No reaction. Because Br minus has no affinity for H plus. It's the conjugate base of a strong acid, hydrobromic acid. If an acid is strong, its conjugate base is weak. No tendency to accept a proton from water. Now, NH4 plus react with water, produce hydronium ion. The solution becomes acidic, because a solution is said to be acidic if there is excess hydronium ion in the solution. pH of the solution is less than 7, acidic solution. pH less than 7. The solution is acidic. 3. Salts of a weak acid and a strong base. What happened to pH of a solution if a salt derived from weak acid and strong base dissolve in water? Now take one of these examples. Sodium nitrite. Sodium nitrite is a salt derived from a strong base, sodium hydroxide, and a weak acid, nitrous acid, HNO2. This is completely dissociates into sodium plus and nitrite ion, NO2 minus. As we said, hydrolysis of salt is reaction of ions of salt with water to produce hydronium or OH minus. Sodium plus water, H2O liquid, no reaction, no appreciable reaction. Because sodium plus is neither acidic nor basic, is neutral. Cations of alkali metal and alkaline earth metal do not react with water. Nitrite ion react with water, NO2 minus plus water gives nitrous acid, HNO2, nitrous acid plus OH minus. Why nitrite ion react with water, NO2? Because nitrite ion is the conjugate base of the weak acid, nitrous acid. If an acid is weak, its conjugate base is relatively strong, can accept a proton from water, has an affinity for a proton. Now there is an excess of OH minus in the solution and the solution become basic. pH of the solution is greater than 7. See? Basic solution. Number 4, salts of a weak acid and a weak base. What happened to pH of a solution if a salt derived from a weak acid and a weak base is dissolved in water? Good. The solution can become either acidic, basic, or neutral, depending on dissociation of the acids and the base. For example, take ammonium acetate, CH3, COONH4. Now this is a salt derived from a weak base, ammonium, and a weak acid, acetic acid, completely dissociates into acetate, CH3, COO minus plus NH4 plus. Both ions can react with water, can hydrolyze. Because this is the conjugate base of the weak acid, acetic acid, is relatively strong, can accept a proton from the donor. NH4 plus is the conjugate acid of the weak base, ammonia, is relatively strong, can donate H plus to other substance. Now acetate, CH3, COO minus plus water gives acetic acid, CH3, COOH plus OH minus. Again, NH4 plus can hydrolyze, react with water. NH4 plus water gives ammonia, NH3, and hydronium ion, H3O plus. Both OH minus and hydronium ion are produced in the solution. Now, the dissociation constant of this base, which is conjugate base of the weak acid, acetic acid, is a base, K base equal K water divided by K acid. K water is 1 times 10 raised to minus 14 divided by K acid, parent acid, which is acetic acid. Its dissociation constant is 1.8 times 10 raised to minus 5. This is 5.56 times 10 raised to minus 10. This is an acid. What type of acid? Conjugate acid of the weak base ammonium. Kn, K acid equal K water divided by K base. K water is 1 times 10 raised to minus 14 divided by K base, the parent base is ammonia. Its dissociation constant is 1.8 times 10 raised to minus 5 equal 5.56 times 10 raised to minus 10. Acid dissociation constants equal base dissociation constants. Implied that equal amounts of OH minus and hydronium ion are produced. Now, this solution is neutral solution. Therefore, if Ka equal Kb, then the solution is neutral solution. Solutions of ammonium acetate is neutral. Its pH is 7. On the other hand, ammonium fluoride is the salt derived from a weak base ammonia and a weak acid hydrofluoric acid. Now for ammonium fluoride, K acid is greater than K base. Implied that excess hydronium ion is produced in the solution and the solution become acidic. pH of the solution is less than 7. For ammonium cyanide, NH4, Cn, K base is greater than K acid. Dissociation constants of the base is greater than dissociation constants of the acid, which shows excess amount of hydroxide ion is produced in the solution and the solution become basic and pH of the solution is greater than 7. Students, in our today's lesson, we discussed common ion effect. Common ion effect is the shift in equilibrium caused by addition of a substance having an ion in common with equilibrium mixture. Addition of a substance that provides a common ion suppress the dissociation of a weak acid and weak base. We also discussed about buffer solutions. Buffer solution is the solution that resists change in pH when a limited amount of an acid or a base is added to it. Buffer solutions contain either a weak acid and its conjugate base or weak base and its conjugate acid. This brings us to the end of our today's lesson. Until next time, goodbye.